and welcome to the screencast where we will model with a sinusoidal function. Any periodic function that has a midline, amplitude, period, and an anchor point can be thought of as a sinusoidal function. So you'll want to remember that a sine function and a cosine function are both types of sinusoidal functions. So we saw in a previous video that if we're given f of t equals a times the sine of k times t minus b plus c, or g of t equals a times the cosine of k times t minus b plus c, then a is the amplitude, y equals c is the midline, and we also saw that the period is 2 pi divided by k, as well as looking at the range and the anchor points for sine and cosine. Keep in mind that the sine function has an anchor point where the graph intersects the midline, and the cosine function has an anchor point where the graph intersects a maximum. All right, so we're going to apply this knowledge to some real-world phenomena. The depth of water at the end of a dock is 8 feet at 4 a.m. and 4 feet at 10 a.m. If the tide goes from low to high tide every 6 hours, write a sinusoidal function, remember that could be sine or cosine, to model the depth of the water in feet, d, is a function of the time in hours, t. So I find it helpful to try to draw this situation. 4 hours, 6, 8, 10 hours. There would be 16 hours. Here would be the depth of the water. So we know at 4 a.m. the depth of the water is 8 feet, and at 10 a.m. the depth of the water is 4 feet. So there's a few things we can identify here. First of all, we can see that the total distance from maximum to minimum is 4. And so our amplitude A is going to be half of that. In other words, 8 minus 4 divided by 2. The maximum minus the minimum divided by 2 gives us 2. We also see that halfway between the minimum and the maximum is 6. So the midline is essentially the average of the minimum and the maximum. So we have y equals 6 is the midline. And then we also see, or are told actually, that from low to high tide is 6 hours. So we saw that in our time from 4 to 10. That just confirms that those were minimum and maximum points as well when we were calculating the amplitude in the midline. And so we need to identify the period. Remember, the period is going to be the length of time it takes to get from low tide to another low tide, or from high tide to another high tide. So if we let another 6 hours pass, we would end up at 8 feet in depth again. So our period is actually 12 hours. And thinking ahead to writing a sinusoidal function, we know that the period, 12 hours, equals 2 pi over k, and we need the k value to write the sinusoidal function. So k is going to equal pi over 6. So we have d of t equals our amplitude 2. Now, are we going to pick a cosine or a sine function? And it really depends on the information you're given. Now, in this case, we are given a maximum value. And we know that the cosine function's anchor point is a maximum. So in this case, it will probably be easier to think about this as a cosine function. So we have 2 times the cosine of k, pi over 6, times t. I'm going to leave some space for the horizontal shift to move the anchor point, plus our midline, 6. And so One thing we want to think about with the anchor point and the horizontal shift is that without a horizontal shift, the cosine function would be at a maximum at time t equals 0. But we want that maximum to first occur at time t equals 4. So we need to shift the graph to the right 4 units, and we'll do that by taking t minus 4. So this would be a possible sinusoidal function that models this situation. Let's take a look at how this looks in Desmos. You'll see here I've graphed the point 4,8 to represent at 4 a.m. the water depth was 8 feet. 10:4 at 10 a.m. the water depth was 4 feet. And since the period was 12 hours, 4 plus 12 gives us 16. So at t equals 16 hours, the water depth would return to a depth of 8 feet. And so if we graph a cosine function with no horizontal shift, just for a moment here, we had our amplitude of 2 times cosine. The k value was pi over 6. We're going to multiply that times t, so there's no horizontal shift yet, and then plus 6, the midline was 6. So we see that the cosine graph has an anchor point at 0, 8, but we need that anchor point to be shifted to the right 4 units so that the maximum will occur at t equals 4. And we know from previous knowledge that to shift a graph to the right 4, we're going to actually subtract 4 inside the function. So if we graph d of t with a shift to the right 4, we do indeed see that this function now models the depth of the water as a function of time. All right, so now that we've verified that our sinusoidal function d of t does indeed model this situation, let's look at the next question. When are the first 2 times that the water depth is 6 feet? And so we just want to recognize that this is actually asking us about the midline. When is the first time that this graph intersects the midline? So here's our midline, y equals 6, and we're trying to find these 2 intersection points. And we can do that by thinking about the symmetry of this graph. So we recognize that from a maximum to a minimum is a distance of, or a time rather, of 6 hours. And because these sinusoidal functions are symmetric, we know that the graph intersects the midline halfway between that time of 6. So we know that this is a horizontal distance of 3. And if we were to work backwards to the other time that the graph intersects the midline, that would also be a distance of 3 away from 4. So the time when the water depth is 6 feet is going to be 4. We're getting that from the maximum, and then we're subtracting 3 hours, so 1 a.m., or the maximum time, 4 o'clock, plus 3 hours, which would give us 7 a.m. And again, we got 3 because that was half the distance, or half the time rather, between when the water was at a maximum height and when the water was at a minimum height. All right, so we're going to look at one more thing with this problem. So earlier we found a cosine function that was shifted to the right to model this situation. And the challenge is, what other sinusoidal functions could model this situation? For example, is there a cosine function that you could have shifted in a different direction? Or, for an extra challenge, how could you have thought about this data as a sine function instead? Give it a shot, and then we'll compare answers. So previously we saw that if we take the cosine function and shift it to the right 4 units, then we can model this data. But we also could think about taking this cosine function and shifting it to the left. So without a horizontal shift, the cosine function would have an anchor point at t equals 12, and we would need to shift that point to the left 8 units to move that anchor point to t equals 4. So a cosine function with a horizontal shift left of 8 units, we see models the data, and that would be written as d of t equals 2 times the cosine of pi over 6 times t plus 8 plus 6. Now a cosine function would be easiest to model this particular set of data because we were given information about a maximum and a minimum, and we know that the anchor point of a cosine function is a maximum. Now, if we had been given information about where this graph intersects its midline, then a sine function may have been easier to find to model this data. Well, we did already determine that the function intersects its midline for the first time at t equals 1. So in this case, we could go ahead now and find a sine function that models this data. We know that without a horizontal shift, the sine function has an anchor point at t equals 0, and that is where the graph intersects the midline and is increasing. As mentioned, we need that anchor point to occur at t equals 1. So we could take this sine function and shift it to the right 1 unit. And then the data would fit, or the model would fit the data. So as a sine function, we could think of this as 2 times the sine of pi over 6 times t minus 1, where that t minus 1 is shifting the sine function to the right 1, plus 6.